Welcome to this lecture which is part of the thermal simulation of buildings lectures, where we talk about the numerical methods that are behind some of the assessment methodologies we can apply. And there are several mechanisms we can use, and one of them is the response factor method, which this lecture is going to be about. We had also previously talked about finite differences numerical methods. So the response factor method is an alternative to the finite difference methods, which we'll talk about today. But both of them are numerical methods. I'll just go over here on the whiteboard to explain a little bit of why we do these things, because it is actually belonging to the lectures about transient conditions for rooms or for whole buildings as such. But those methods, both for the finite difference method and also for the response factor method that we talk about now, they are dealing with the walls. So really we should make a heat balance for the room or for the building rooms. But very much the heat exchange with the walls are important to describe the transient development of the temperatures and heat flows in our buildings. So just briefly to illustrate or to recap what the lecture with the finite difference method did, it divided the walls into some finer volumes for which we made, in each volume we had a node point where we calculated the temperature. But this I will not recap, you have to see that lecture separately. But that is mainly to illustrate the alternative today where we talk about response factors. We can use analytical theory for a wall of finite difference, a certain thickness of the wall, where if the wall is exposed to some temperature impulse on one of the sides of the wall, well, then we can see what is the result of the heat that flows into the wall and what flows out of the wall. Analytical theory covers everything what happens within the wall, but we are going to use some response factors for those impacts and the responses in terms of temperature impacts and heat flow results as that responses. So let's go back to the slides over here to explain a little bit more what it is. And now I've become a little bit more fundamental in it to say that, well, for the response factor method, a fundamental principle is a superposition. And conditions for that is that we have linearity, which essentially means that if we have several responses, well, then we can add them up. So for instance, if you have twice as large temperature impulse on a wall, then also the heat flows will double. That's in principle what this says with the linearity. The other thing is the invariability, which means that the effect I make today on a wall will have the same effect if I study this tomorrow, to say it briefly. So the time that things happen it doesn't matter so much. We can add things up. So for superposition altogether, we can summarize this. I'll read it out. When a system is exposed to a number of influences, the effect of each influence is independent from the other influences, and the total response is the sum of responses of all those independent influences. And that we'll just show now in a little bit more mathematical way or illustrated somehow. So here's my wall from before. And we have a left hand and a right hand side of it, of course. And what we do is that we suppose now suddenly we have a unit increment of the temperature on the left hand side of the wall. So it starts from an initial temperature and suddenly this thing happens on the left hand side. So what will then be the result of that? Well, of course, we'll have heat flow into the wall. So we have heat flow coming in and also heat flow coming out. And what we can see here is that there is some time delay for the heat flow to pass through the wall after this unit step of increasing the temperature on the left-hand side. We could also have another condition that what if that increase in temperature lasts only for 1 unit of time, 1 hour, for instance? Well, then the response on the other side, it'll of course increase, and then it'll decline again. So that's the response, and that was the impulse that we put on the left-hand side. We could also look to other impulses. So still kind of a unit impulse. It has the height 1 degree temperature, and it has a duration 2 hours, but it increases like a triangle. So the area is still 1 by 1, you could say, a unit impulse here, but in the shape of a triangle. And this we very often use to represent if we want to have a temperature curve on the, let's say, left-hand surface of the material, which really goes continuously like this, well, then we can try to approximate that by a sequence of triangular impulses like this. So here's just one of the impulses that is marked here for one of them. But if you add those up all together, it becomes a rather good approximation to the real continuous temperature influence that we had on the left-hand surface. So now, studying again the wall, what we do, mathematics takes care of what happens inside. You have to look back to analytical theory, or some people have done it for us. Then we know if we have temperature impulses on one side or on the other side, then we will also know about the heat flows on the same sides or on the opposite sides. And that's the whole point to it. So we have 4 variables of interest, 2 temperatures, one on each side, and also 2 heat flows, one on each side. So now let's look to the whole methodology of calculating this. So we work with these triangular impulses. Let's assume that we could have one coming from each of the sides of the wall. Well, if we look to the first impulse that came on the left-hand side, well, then we have some response factors. And the X factor tells us what is the heat flow coming into the left-hand side of the wall as a result of the temperature impulse on the left-hand side. We have also a response factor on the opposite side here. So this tells us what is the response as a result of the temperature now on the right-hand side. So it's always the X factor is for the left-hand side on the same side as that impulse, and the Z factor is the response factor for the temperature on the right-hand side. Also, we see these response factors, they are themselves time-dependent functions. So it tells us how we have, as a result of the temperature impulse on the left, first we have heat flow going into the wall, which is in the positive X direction. So we have a positive X factor in the beginning. After a while, when the temperature impulse stops, well, then the heat is flowing back to where it came from, so to speak. And then we have a time sequence with some, well, smaller, but they are negative response factors. And we see the same on the right-hand side with the opposite sign in front of it. So also we have heat flow going through the wall. So if we take again the exterior impulse of temperature, well, then the heat that comes out on the right-hand side of the wall as a response to that, that is explained by the Y factor. And it's a much lower value, and it's slower like that. But we have, again, a time series of the Y factors. And the same Y factors with the opposite sign tells us about the heat flow going out on the left as a result of the temperature impulse on the right. Okay, so now we have response factors as time series for the different impulses on the same and across on the same side and across the wall. And we can add them all up on either of the sides and get some total responses when it's added up, like we can show it here. So if we can calculate those response factors as time series, looking to the theory how that should be done, it's a very efficient way to calculate heat flows in and out of walls, when we calculate this in the conjunction with the whole building, as I indicated before on the whiteboard, is the purpose for what we do. So the idea is that we use these time series of impulses and response factors on those sides of the walls. Then we can find the heat flows going in and out and how that influences our rooms and so forth. And we scale the whole thing. So we work with unit impulses, and then we can scale it by multiplication with the real temperature impulses as much as they are if they're not only 1 degree high. And everything is then added up back in time with all those time series. One thing is that if we have a temperature impulse on a wall, theoretically it'll last forever. But in reality, things die out. So we need only remember the time series, the X factors, Y factors, and Z factors for a certain number of hours, typically. So that therefore it's somewhat practical to calculate this. We can write it all up mathematically. So, and this will be my last slide. But here the heat fluxes, they can, on one side, as a function of temperature, it's a summation of the temperature impulses that we had on one side times the X factors, that time series of X factors on that side. We add up infinity, in principle until infinity, but in reality only a certain few number of hours. And then we should subtract what comes, the impulse from the temperature on the other side of the wall, multiplied with the Y factors that are across the wall going, so to speak. And then we do the same for the other side of the wall, the right-hand side of the wall. in similar writing, so I'll not repeat again exactly what it says here, but it's a summation of those factors with the temperature in pulses. So we should have the X factors, and I've said it already, but count them back in time and number of hours and remember those. Y factors are needed as well for the cross-going influences. And then we have, of course, the Z factors, which are quite similar to the X factors on either the left-hand side or the right-hand side of the wall. Those are our response factors, which are the factors that have given name to this method here. T, of course, is time. Q are the heat fluxes. So this is just in summary. And then we find also the temperatures on our walls and in the rooms. So that was a wrap-up of the whole thing. And that's some indication how to understand the function of the response factor method, which is a very common method used in building analysis tools because it's rather efficient once those factors have been defined. Thank you for listening in. I hope you enjoyed this talk also. Thanks.